Hello, everyone. We're going to get this panel started. Thank you all for coming down and joining us. We have a long panel. It's about an hour and a half, so feel free to come and go as you need to. But I hope you stay. We have some really great panelists and really good discussions following the presentations this afternoon. But we're glad you guys are here and here with us today. My name is Brendan Langenheisen. I'm the Director of Technical Advocacy at the Colorado River District. We have been involved not so much with the technical side of soil moisture, but with a lot of people coming to us. So our district covers, here's a picture of our district. So it covers 15 counties in western and northwestern Colorado, all within the Colorado River Basin. And this topic has come up a lot, especially within the last year, of soil moisture. So from all different angles, this long 22-year drought, aridification, has really brought this topic up. And people are interested. And it's brought up mainly because there is this question of unknowns. What is going on with soil moisture? Where are we? We need more data. Can you help us? Or can you help fund this project? Or and I've listed some of these project themes that have come up to our district, all regarding soil moisture, and that was the impetus for today, of really trying to build that collaboration. And just what is going on with soil moisture? Where is the science today, and what is happening on the within our district on the west slope of Colorado? And so, real quickly for forest health, using soil moisture to look at the health of the forest, maybe look at long-term drought conditions in the forest, or possible fire danger, climate change impacts, watching how are the ecosystems changing as we get drier. We're getting different vegetations, and how is the environment changing. Post-fire safety and recovery, so we have a speaker today to talk about that, of looking at Glenwood Canyon. We had a lot of debris flow events, and how do we monitor that? How can we better predict when those are going to happen? As well as looking at recovery. How does restoration of these fires occur, and using soil moisture to help modify that? How much water is actually making it down into those root zones that really help with that restoration? Agricultural operations with regenerative ag, or how do you build soil capacity, has been one of those questions. As well as how do you operate, when and how much water do we need to apply for those crops? And one of the big ones is snow to flow. We are seeing a lot of these basins. This is just a recap of last year, where we're getting these averages. We're hitting like a certain percentage. So this is last year, a certain percentage of average of snowpack, but our runoff isn't matching that. It's not a one-for-one correlation, and this has been a pattern that's happened over the last couple of years, particularly. And how much of this is derived from soil moisture? We've had really dry soils going into the falls, and how much of is soil really going to impact these misses between take the Colorado River. So 90% of average of snowpack, but the Colorado River down at the Cameo gauge received and saw about 80% of average snow of river flows. And so what is that missing? And soil moisture is probably not the only thing going on. There's probably a lot of others. Is it sublimation? Is it differences in where snow's falling to begin with? Or better, we just need better snow measurements, or it could be a whole number of things. And so, but soil moisture is part of this conversation. And so really trying to see and improve this data. Where are we, and what efforts are out there, and can we build that collaboration as we're starting to develop more of these systems? How are we talking to each other and between the different agencies to capture that data and use that data? And so that's a lot of what our panel is. And so, oh yeah, I had a couple more slides. So here's some monitoring soil moisture locations. So this is just the NRCS. So this is where the NRCS is. They'll probably have the largest network in Western Colorado. And you can kind of see that's just the current situation of where we are as of September 1st. Other people have programs. The Forest Service, the USGS, Colorado Climate Center has through the COAGMAT stations. NASA has some satellite imagery that's looking at soil moisture. There's a lot, and there's a lot more. I was just listing some of them, but and some of them you'll hear today of maybe some of the smaller networks. But who's monitoring and where are those stations? Where are those stations? And so this, I just wanted to show you how some of the disparity is and where these stations are. There's a lot of space not covered. And again, this is just the US, or just the NRCS, but how do we add some more granularity to this? How do we add more data to really cover what's going across the watershed rather than just either in the highlands, up in the mountains, or basin to basin? Because in the, just for instance, so looking at the Colorado River Basin right now, they have colored that red, and that's based off of only 2 stations, 2 active stations for those parameters, the 8-inch soil moisture status right now. And so there are, even of those gauges, how many of them are actually used, are up and running, and are able to help with some of these predictions and characterizations of our basin. So what's coming, and this is what this panel is, we're going to hear about from each of these panelists, what are they working on, and where are we going? What is the collaboration that we can have? And so this is what today is all about. We are going to have some presentations from all of our panelists. So we have 4 different panels. And then we're going to have some discussions about some of these things. And I hope you guys can be thinking about some questions. So there's a decent amount of time at the end for that dialogue and the discussion. And I hope you guys will participate in that. So today, our panelists, we have Ryan Banta from the USGS. So he is going to be talking about their program on Grizzly Creek Fire and the debris flows there, as well as a couple other USGS programs that are going on. Then Elise Osenga will come up, and she is from the Aspen Global Change Institute. And she's been running, she started and is running a network throughout the Roaring Fork Valley, a soil moisture monitoring network. Yampa Valley Sustainability Council, right? Okay. I was like, you get up here and you get nervous, and you're like, is that right? So Madison, Muxworthy, and Nicole Pepper will be talking about a program that they're just getting up and running. And then we have Kerstin, Paulsson, and Duncan Axisa from, Center for Western Weather and Water Extremes, so CW3E. So you'll see that referenced here in a little bit as well. And so all these guys will present, think about some questions as they're talking. Afterwards, they'll come up here and we'll have a good discussion. So yeah, thank you. And here's Ryan.
First one. Clicker?
Oh yeah, that would be helpful, huh?
Thank you. Excellent. Good afternoon, everybody. My name is Ryan Banta. I'm with the U.S. Geological Survey. Testing. I'll use my deep voice. I am Ryan Banta. I am with the U.S. Geological Survey. I'm the Hydrologic Studies Chief. I'm based out of Lakewood, Colorado. But that is just home base because we are doing soil moisture and hydrologic studies across the state. And what I wanted to do this afternoon is just highlight what we're looking at in a post-wildfire scenario, specifically at Grizzly Creek the Grizzly Creek fire, and the watersheds that were burned and unburned in that immediate area. I'm going to be quick to point out that, yes, I'm with the USGS, but this cannot be done without a whole host of stakeholders support, both local, state, and federal partners on this, both internal USGS as well as other federal partners. So a big shout out. I couldn't even list them all here if I wanted to. There are many hands to make light work on this particular project. So for those in the room that are not familiar with the Grizzly Creek fire, just a very quick background, and that is simply in 2020, half of Colorado burnt down, or at least that's what it felt like. And Grizzly Creek was one of those. It was not as big as the East Troublesome or the Cameron Peaks, but it still made the top 20. About 32,000 acres were burned. And what was unique about this one is it was right along the Colorado River in that valley on both sides of it. And given the steep topography and the canyon that it was in, when the USGS hazards team came back through and said, okay, what's the likelihood that we're going to see some debris flows in this particular area? This whole area lit up. Let's see, do I have a pointer on here? No, that's okay. You can see in the dark red, those are sub-watersheds with a likelihood of 80 to 100% likelihood. If you have a design storm going over the top of it, are you going to see a debris flow or not? And there's a lot of red in there. And so people were really concerned, what are we going to walk into in 2021? Fortunately, this happened in August of 2020, and so we were just on the tail end of the monsoon season. Come 2021, everybody was asking the question, what's going to happen? And this project started out as to what's going to happen with water quality, because this debris is going to go into the Colorado River, and there are a lot of people that use this as a water supply. And so the first question that was asked was, what's going to happen to the water quality, and is it going to change? And so we said, okay, well, let's start with this question as the network, and we'll do a two-prong approach. The first one is looking at synoptic sampling. Basically, these are snapshots in time. And for that, let's look at some tributaries in the burned area, specifically Grizzly Creek and No Name Creeks. But let's also look at Mitchell Creek, because that was an unburned area, and see, one, is that going to flow, and two, what kind of contributions that would have. Most importantly, though, we have a site in the Colorado River right above the Roaring Fork confluence. That's kind of like the integrator site to say, all right, so sum total, what are the effects of fire? The problem with the synoptics is you have to be out there sampling at that time. And we all know that monsoons come in on a Saturday night at 2 a.m. on the 4th of July weekend when nobody is out there. So consequently, we wanted to put some continuous sensors in the river itself, specifically on the main stem. And that's to look at what we call the big five, which is temperature, conductance, turbidity, pH, and DO. We also put in some FDOM and some other more, I would say experimental, but really a little bit more cutting edge and innovative type of sciences. Nonetheless, the idea is to build a network. So we're going to leverage where we already have existing data and then add to it. What that looks like spatially is, on this map, the triangles are the continuous sites, the circles are the discrete sites. And again, you can see right along the base, right at the base of the Grizzly Creek and the No Name Creeks, that's where we're collecting our samples from. So it's going to be that entire watershed that will be represented. Nonetheless, this was the beginning of the questions. And we were all poised. We collected some samples before the runoffs, after the spring snow melts, and then we're coming into the monsoon seasons. And oh my gosh, did we have a season in 2021. For those of you that were locally here, we had a record, well, I believe a very high number. I don't know if it's actually a record number of debris flows, but I-70 closed multiple times in both directions. And the question is well, what is those effects that we're seeing downstream? Here's what's really exciting about this. This is a plot of turbidity over time. It's a 2-month period on here on your x-axis, and you can see the individual storm events as they're coming through. Don't worry so much about the numbers. The simple fact is about 3,000. That's about the limit of what the sensor can actually see. And so what it's saying is you've got chocolate milk coming through the system on here. And we were able to get out and collect some of the samples during that time. Now, I'm belaboring a little bit on the water quality aspect, because at the end of this, they said, well, that's nice, it's water quality. We need to get in front of all of these debris flows. And so they asked us to install 7 different MET stations up along the ridge lines so that they can have a little bit better predictive capabilities. And so we were working very closely with National Weather Service, trying to look at the other components of this hydrologic cycle. The big question is what else are we missing? And everybody in this room knows that soil moisture is one of those big unknowns at this point. You can see the effects of the debris flows. You can see the effects of the monsoons. But is there a way that we can predict a little bit better? And so for that reason, soil moisture was added last year at 4 of these locations. Now, they were installed at about 10 centimeters deep in the undisturbed soil. And the reason why we chose 10 centimeters is because when fire came over the top of it, it turned the top little layer hydrophobic, essentially. It's a common practice in really hot and severe fires that organic layer in the top layer of the soils will basically plasticize, and it turns hydrophobic. And so as a result of that, if we tried to put the sensors right in that top 1 inch or 2 inch area, we were worried we're gonna break up or disrupt that hydrophobicity, and so the measurements wouldn't be as representative. So the point of this particular network is to be able to get underneath the hydrophobic and see what is penetrating all the way through. So we chose 10 centimeters. We are collecting data about every 5 minutes, which seems a little bit of an overkill for soil moisture. Nonetheless, when the intense monsoons come through, it's actually really interesting to see how quick or not the various sensors respond. Because we timed it, or we linked them into our precipitation network, we already had telemetry. And one of the neat things that we as the USGS do is any measurements that we make, we try and put on telemetry so that we measure it in real time, send it out every 15 minutes to every hour via satellite back down to our servers, and pump it right out onto the National National Water Information System database. Basically, NWIS, for those of you that are familiar with it. You can go to any of the USGS streamflow sites or any of these precipitation sites and soil moisture, and you can see the current conditions within the hour. And so when you're trying to do predictive capabilities or ingest data from the National Weather Service, and they're saying, do I issue a warning here? Do I not? Is this a go, no-go type of a situation? They need data as quickly as possible. And so that was one of the missions that we wanted to do, is get this data in the hands of the people that could use it. I'm gonna re-emphasize the collaborations on this aspect. Yes, National Weather Service, it was a big one from a predictive capability. And again, that is all in their bailiwick. We don't do that. All we do is provide the numbers, and then they use that and they say, based on those, these are the next steps. Similarly, we're collaborating with the U.S. Forest Service because they have some remediation techniques that they're going to be using for vegetation types. So what type of mulch are they going to put over there? What type of vegetation recovery techniques are they going to implement? And so they've got some test beds is the best word for that, where we're working with them so that they can better not only ingest the data, but then predict what kind of vegetation recovery are they gonna see in 3 to 5 years. Our hazards group, obviously from debris flow predictions, they're gonna wanna be able to do some hindcasts and say, gosh, if we had soil moisture in year 1, would we have changed the maps? Would we have been able to predict different type of flows, where they occurred or how frequent? So the locations that we chose for the soil moisture are highlighted here in yellow rings, and they're largely up on the ridge tops. That is largely because of access issues. It's hard to get into some of these canyon sites in here, certainly to be able to service some of the gauges. But that's also because of the way the monsoons and the weather patterns are coming over the top. The ridge lines, basically the orographic effect as the storms are coming up through canyons or coming over the top, you're gonna see a lot of precipitation along ridge lines. And so for access and other reasons, those were selected. And what, oh, come here. There we go. And one of those sub-creeks, I wanna highlight specifically some of this hydrophobic layers that we've been talking about. This is a video that was taken shortly after the fire by a colleague in the USGS, the hazards. And this is up in French Creek in the burned area, and he's dropping a little bit of water from just a normal water bottle in there on the surface, and you can see none of that is going in. Here comes another little setup there right over the top. This particular little batch, he just put a timer on there to see how long this little bit would take to actually absorb into the soil. 35 minutes later, that little pool disappeared. 35 minutes. Now imagine a design storm which comes in with 24 millimeters of rain in a 15-minute period. That's a relatively intense storm. The ground's not going to be able to absorb that. That rainfall is going to hit the ground and it's going to come right over the top. So this is the conditions that we're in and that we're experiencing. Consequently, we now have the soil moistures. They are installed. We've been monitoring it all summer. We've seen some of these monsoons come over the top. And the question is was that me? Timing. What do we see in the subhydrophobic layer? This is just a small snapshot of a week period on here. And in red is the precipitation event. And so you can see as you're coming along your x-axis, there's no rain. You have a little monsoon. You got basically a half an inch of rain come down, a little break, another half inch, a break, half inch, and then your last half inch. So 2 inches over a roughly 2-day period. And soil moisture here is in the blue, and it kind of bounces around nice and low. The first 3 little rain pulses, it does not respond. It isn't until the last pulse that soil moisture finally goes, all right, I've got enough to be saturated. And so you can see the effects of the rain penetrating down through that top layer. Again, we are just unpacking this. This is from August of this last year. So this is really hot off the presses. Next year at this conference, I'll share out and say, and this is what we saw spatially and temporally in monsoons, et cetera. But this is just to kind of whet the appetite. We are really excited that we're seeing these type of dynamics within the system. Now, this is in the Grizzly Creek. I'm going to shift gears slightly because we've got another program within the USGS called NGWAS, and that stands for the Next Generation Water Observing System. And essentially what happened was Congress allocated out some funds and said, USGS, you're doing a great job of monitoring stream flow and water quality and all these other aspects. However, if we gave you a slug of funds, could you up your game? And that could either be denser spatial footprints. So you've got a site, way up in the headwaters and way down in the confluence, but do you have anything in the middle? And then said, do you need to redensify based on some data gaps? Or do you need to take your technology and if you had an influx, basically get over your initial hurdle and be able to use more innovative techniques to get at the same type of questions? So an easy example of that is using radar and velocity measurements to be able to measure stream flow. Well, that also comes into play when you're looking at soil moisture. And so we've got a project looking at soil moisture of the technology bump, if you will. And we're using a whole bunch of different type of sensors. We're testing out new technologies. One of the big ones is looking at the flux of cosmic rays and the measurements of basically the hydrogen ions to be able to quantify how much water is in the immediate surrounding area. And that includes the subsurface. If you want to know all the details, come talk to me afterwards. I've only got a couple of minutes here, and I promised Brandon I wouldn't go off the deep end of the science. Nonetheless, I'd be happy to talk shop on those aspects. But I just highlight that as this is an example of how we want to be able to push the soil moisture question and be able to answer it not only spatially but innovatively versus just sticking a couple probes and you got a couple point sources, but getting a larger integrated footprint. Right now, the test beds are in the upper Colorado, but there are more sites across the United States that we're looking at this question. The next part of it, though, I need to highlight is the snow component, and this is the snow to flow. As Brandon just mentioned, the snow is driving a lot of the hydrology in Colorado, and the snowpacks are behaving a little bit differently in recent years. And so we want to really be able to get at the snow water equivalent. And then with that snow water equivalent, how much of that is actually making it into the ground? So we're putting in a bunch of new test bed locations, and as a part of those test beds, soil moisture is a really important piece of that overall hydrologic cycle. As you can see by the pictures in here, this is during the springtime versus when it's actually buried in snow. There are more than one sensor out there. This is actually really fun data sets. Again, I'm happy to unpack this afterwards from a little bit of a talk shop. I'm gonna throw this slide up here just as I'm wrapping on up to say, where is this occurring? We've got a couple test beds right now. One of them is up in the Fraser Basin, kind of near Winter Park. Berthoud Pass is another one. We're looking to put in some more snow stations, 3 locations specifically, and a whole bunch more soil moisture networks because we need to get that spatial density. That's that NGWAS part of it that I was talking about. It's not just innovation. We need a bigger footprint and a better representation. This is a slightly older slide in the sense that we were talking about different type of networks of how many sites, of starting them out, then reassessing, then make these ones permanent, and then check out some other areas. Because of permitting, permitting is always something that needs to be contended with. And so we've adjusted this slightly to say, if you've got a good area that's representative, come talk to us because we are very interested in getting as many sensors out as we can. Nonetheless, this is a map of some of the initial aspects that were proposed. And you're gonna hear momentarily that some of those are gonna move forward up here in the Roaring Fork. So I'm gonna wrap up and simply say, the USGS, our goal is to provide the best data we possibly can and get it out into the decision makers' hands as quickly as possible. And then what you do with those data sets, that's the decision makers. USGS just does the science. But to give you the best science possible, we need to look at the networks that we have in place. And 2 of the main networks that we've got building right now is a post-fire situation, not just here in Grizzly, but we've got one up in the East Troublesome, all the way down to Pine Gulch Fire, just from Colorado. But California, Oregon, Montana, New Mexico, they all burnt too. And so the USGS counterparts out there are doing the same type of approaches. So our goal is in a couple of years to be able to put all these data sets together over a couple of year period and say, okay, so what were our lessons learned? That being said, NGWAS, Upper Colorado is one of 10 basins as well. And so there's one out in Delaware, one in Illinois. The Willamette was just identified as the 4th. And every year they're gonna add a new basin to this network. So again, networks and having that spatial density is really key, but so is the innovative science. But at the end of the day, it comes down to working with the stakeholders. And so I said at the beginning, I'll say it at the end, thank you to everybody, because the questions that keep coming up are, what do we need to be measuring now before a burn or before a catastrophe or before whatever? And then what should we be measuring post-event? And soil moisture has not been a part of those big conversations because debris flows, quite honestly, have a bigger immediate impact. Soil moisture, though, I think could be one of those hidden components that starts unlocking a lot of the science. So that being said, I'll open it up to questions at the end.
Great presentation. Thank you, Ryan. All right, on to Elise Osenga.
Hi, everybody. I'm glad I get to follow Ryan because I think he covered some kind of technical stuff that now I can just reference back to quickly. I'm Elise Osenga. I'm with the Aspen Global Change Institute, and I'm here today to tell you about our long-term soil moisture monitoring program, which is called the Roaring Fork Observation Network, or IRON. And this is really, at its heart, a story of collaboration, which fits with my organization as a whole. So AGCI is a nonprofit that's dedicated to the science side of advancing global change science and solutions. And we do this by acting as a bridging organization. So we're connecting researchers across different fields of discipline, but we're also sometimes connecting researchers directly to decision makers. And that's how this project originally got started. So there was a workshop in 2011 held in Aspen on forest health. And there was this question about, with climate change happening, with pine beetles coming in, what do we need to do to better understand our forests so we can better protect them? And the folks at this meeting were a mix of decision makers, people from the county and city, some educators, and then a whole bunch of different scientists who look at problems from different perspectives. And they came up with this recognition that what we really wanted, as far as the decision makers were concerned, was to understand the impact of warming at a local level. And that in order to do this, we needed to monitor key ecosystems for changes, relative to different land management questions, but also relative to where they fall in the elevational gradient, because what happens in the mountains is very dependent on how high up you are. And that we also needed to understand connections across physical systems. How is what's happening in the atmosphere impacting what's happening in the ground, impacting what's happening in the water, impacting what's happening in the plants? And the repeated item that kept coming up was soil moisture. but there isn't a research university physically based in the Roaring Fork watershed. And so folks came to AGCI, who was the host of that meeting, and said, well, would you guys be interested in starting a long-term monitoring program? And we said, sure. So we put in our first 2 stations in 2012. The first one started collecting data that same year. The next one started collecting data in 2013. And what happened over the following decade is that those 2 little stations grew into an entire program, the Roaring Fork Observation Network. And we sort of re-envisioned our goals a little bit. So we realized we wanted to advance understanding not just of ecology, but also of mountain hydrology, that we wanted to build community among data researchers and data users, and also across different watersheds, because a lot of the issues we're facing in the Roaring Fork are parallel issues to what's going on in other places like the Yampa. And then finally, we wanted to make sure that this data we were collecting wasn't just of interest in a basic research capacity. We wanted to make sure it was decision relevant to resource managers. And we wanted all of this to take place in an awareness of what are the climate change components that are influencing these different things we're looking at. So soil moisture was the unifying factor for all of this and was the main metric that we said, all right, this is something that really hasn't been studied much outside of agriculture. When you saw the map Ryan put up, there weren't a whole lot of dots for something that is this important. And I have a quick question for you guys. Raise your hand if soil moisture is a term that you hear on like a monthly basis that shows up in your work. All right, most of the room. Raise your hand again if soil moisture is a term that you hadn't really heard or thought about in a meaningful way previous to 2 years ago. Previous to 5 years ago? Previous to 10 years ago? Okay, so what we're seeing is this is something that is increasingly getting talked about. So when I think about soil moisture, just to give a quick definition, I think of it as the amount of water held in the soil at any given time. And I'm thinking about it from a number of different perspectives. The role it plays in plant survival and determining what species can live where, the role it plays in things like near ground temperature and microclimates, the fact it's a major player in flood and fire risk, that it determines runoff volume, so what we are getting at in Ryan's presentation with that snowpack to stream flow question, how much runoff you have is very dependent on your previous year's soil moisture, and then it creates this drought memory, so we're in this multi-decade drought right now, and so soil moisture is getting a lot more attention in recent years because all of a sudden it really matters that last year was a severe, severe drought compared to whether or not we got close to average snow this past winter. So this is where I work looking at soil moisture, the Roaring Fork watershed. And it's a fairly small watershed in terms of just geographic area. It's only about 1,400 square miles large. But it has a really outsized impact. And it's also really interesting because it's got a lot of heterogeneity. It's got a lot of variety within that basin. So we have elevations as low as 5,800 feet at the confluence with the Colorado River. And we have mountaintops that if you can jump high enough when you're on top, you'll reach 14,000 feet. But in spite of the fact that it's not very big, it has this really big role as a headwaters area. So it covers about 0.6% of the land area of the total Colorado River Basin, so all the way down to the border. But it contributes 6% of Colorado River flows, so that's a pretty outsized impact for its size. And in addition to that, almost half the water that would normally be running down the Roaring Fork is pumped up and over the Continental Divide to the Front Range. So if you are out in Pueblo or out in Denver, you might be seeing some water that came from the mountains somewhere else. So what happens up here is really super important. And when we were setting up our network, we wanted to make sure we were capturing both that elevational variety and the ecosystem variety across our watershed. So our stations have everything from dry scrub oak zones all the way up to alpine willow. And here are those 10 sites. So over the years, we've added a couple sites every year till we're now up to 10. Our earliest site is the third one from the left, up in the Aspen Grove up there, that's Sky Mountain. It was put in specifically to look at aspen trees and what was happening in that grove up there because it's sort of an inholding of aspen amongst the scrub oak. And then our most recent station went in 2019. It's also our fanciest station. This one is Castle Creek. And it, like I said, started up just quite recently, but was one that we added a lot of different things to measure snow metrics on. So a typical station for us measures these variables. It has a tipping bucket rain gauge. It captures relative humidity and air temperature, soil moisture at 2, 8, and 20 inches. So to give you a reference for Ryan's depth, that's going to be 5, 20, and 50 centimeters. And then we have soil temperature at that middle depth as well. And they're all powered by solar panel. Most of them have a cellular connection. Some of them have a satellite connection. And all of these data are publicly available. Some of our sites additionally have snow depth and wind, and one of them even has radiative balance, which is basically a quick way to see if you're having dust on snow events. And this network, this 10-station network that spans the entire watershed, was possible because of partnerships. So when I said at the start this is a story of collaboration, it's been a story of collaboration from day one. The original funding came from Pitkin County, and support came from City of Aspen and ACES for those first 2 stations. Since then, our partner list has grown and grown, and how they help has changed too. It's everything from funding to committing expertise and getting out in the field and sharing knowledge about botany or soil science, to giving land use permissions, which can be very hard to find in an area where most of the lands are public lands, to engaging with the outreach and communication, to the local community college that has an internship program that we partner with so that these students can get fieldwork experience. And really, when I say this network is not possible without this partnership, it's also not meaningful without these partnerships. Because from our perspective, the basic research is nice, but the ultimate goal is to get information back into the hands of decision makers, because this is such a dry region, and it is so critical that we understand what is happening and how the temperature warming we're already seeing is going to change our water supply and going to change our ecology. So what kind of things do I talk about with those stakeholders? Overall, this is a long-term project, and a lot of the questions that we're helping to answer are questions that really can't be answered until we have several decades of data, because we're looking for long-term trends. But in the meantime, we can start to better understand some of the patterns that are going on where we're at. So this is a graph of our deepest soil moisture sensor up at Independence Pass, which is a 12,000-foot elevation above tree line station. And I chose this one because we know that those really high elevation areas are some of our most critical areas for water supply. And the kind of things that we can see looking at a graph like this are patterns across the year. So this is a water year. We're actually starting in October and moving through September of the following year. And what you see is over winter, the soils tend to be pretty inert. They freeze, and you don't really get a lot of water in or out. And this is what plays into that question of how much runoff you get from snow. So if you have really dry soils when you're heading into winter, what happens is when your snowpack melts out, those soils can take up a much larger percentage of the snowpack than they would if you had really wet soils when you headed into winter. So as we're heading in this year, that's something that I'm really interested in, is looking at, all right, how are we looking at this specific site? And I'm gonna say, these sites are very different from one another. Some might be wetter this year than last year, some might be drier, some might be about the same. But at this particular site, 2022 in gold is looking wetter, thank goodness, than it did in 2021. So that's what I mean when I'm talking about drought memory. When you have dry years, that's gonna impact your runoff the following year. And you also see things like, when did your snow melt out? Because typically at high elevation sites, the final snow melt ties into your peak soil moisture value before things start drying out before spring. And you can see 2021, we had a very, very early start to the melt season at Independence Pass. And that matters in terms of when you're gonna see your pulse of snow. It matters in terms of your fire season, all different kinds of things. So even though we can't really talk about some of those long-term trends yet, we can already start to say, how does this year compare to last year? And we can also say things like, recognizing the importance of intensity of rain events and what level of intensity is necessary for water to get down in different types of soils across our watershed. So we are 10 years old. We've been looking at and thinking about these things for 10 years now, which is really exciting. And the next step for us is thinking about, how do we work and build on all these collaborations we've had in the past and this now 10-year data record from our oldest station and the incrementally smaller data records from all the more recent stations to move forward to make sure that we're really staying on track for making sure this is a valuable project. So the heart of the project when we first started was the ecological research questions. And we want to make sure we continue to keep an eye on those because, like I said, those are the original driving force behind this project. But these are long-term questions like, are certain plant species moving or are other plant species becoming dominant as we're seeing these changes? And what's driving that? Is it air temperature? Is it soil moisture? how can we use our data set to help understand those things so that when land managers go back and are making decisions about what they want where, they can do it in an informed way. And just like Ryan said with USGS, we're a little bit similar. We're not going to tell someone what to do, but we can at least tell them what the landscape they're working on looks like. But then in the meantime, while we're waiting for that long-term data record to build up, we had this recognition that, oh my goodness, soil moisture matters for hydrology as well. Who would have thought? So this is just a very basic diagram to reiterate this idea that when you're in a place where your snowpack might be between 60 to 80% of your water supply for the year, knowing how much of that snowpack is actually going to end up in the river versus getting taken up by the soil or lost in other ways is a really important question. And so this is kind of a central focus for us as we're thinking about our research questions in the hydrology realm for the next 10 years. So our key hydrology research questions in our strategic plan are: how will climate change impact water availability and water supply timing in the Roaring Fork watershed? And then a kind of companion question that's going to help us answer that is, how is the water split between the snowpack, the soil, and the streams? And how does that split, how does that partitioning change throughout the year? And different timing of like intensity of when your monsoon moves through, how does that play a role? And then finally, a question that I'm going to reiterate when we get to the panel discussion in this group is, how can in situ soil moisture data be assimilated into water supply forecasts and models? So to put this in really simple terms, the soil moisture changes from one footstep to another across our basin. So if we're measuring at single points, and if there are other groups who are also measuring at single points, how do we leverage that single point data to be as useful as possible in understanding the big picture of things in such a way that we can make sure that the forecasts and models that water suppliers are dependent on are as accurate as possible, or inform them in other more qualitative ways. So to do this, there's a lot of different things we're going to be doing. This is just a very, very short bulleted list, and I'm actually going to summarize it even more briefly and just say, in order to answer those questions, we need to make sure our data record is continuous, but we also need to make sure it's robust. And we need to be able to figure out how can we make comparisons between our little single point stations and bigger, broader things that are going on. And there's kind of two exciting components I want to mention that are coming up in the very near term. One is the NGWAS, as was mentioned before, has selected the Roaring Fork watershed to be one of its test basins. So we're working closely with them, in some cases co-locating their instruments and our instruments so we can validate back and forth and see how this cosmic ray sensor compares to our physically in the ground sensors. But they're also going to be picking certain basins that aren't yet covered by our network, which is great because in terms of funding and management and just practicality of getting stations in the ground, it can be difficult to add stations to a network. So being able to leverage someone else's funding and availability and co-share that data is really helpful. And then we're going to be working cross-basin as other catchments start up their own soil moisture networks. So you'll hear from the Yampa folks about that. And as we do that, we're going to need to be thinking about how do we compare our own data. So this leads me to my final slide, which is, what does partnership look like and mean? Throughout this project, we've been dependent on partners, and that's only going to be more true as we move forward. So in thinking about the context of soil moisture is something that there is increasing demand for. Folks are saying, we know this is important. We know right now a lot of times it's represented in models or forecasts as a black box or as a proxy where you're using other factors to guess what your soil moisture might be. As we want to start having actual physical on the ground measurements, that's going to be most valuable if we're coordinating those efforts. So this is my wish list. I want a way to compare my data to everyone else's data, whether that's having to deal with the fact that different soil types behave very differently, or we might even be using different instrument types for a variety of reasons. So figuring out how do we kind of normalize our data so I can talk to them and they can talk to me and we can share that with other folks and be able to talk in a way where we're using the same language when we talk about it. I want to be able to compare our data to things like satellite so we can start to project how do our little single point measurements compare to the big picture of the whole watershed and vice versa so that it can be as accurate as possible. And we'll need centralized places to communicate, whether that's communicating with one another so we all know what research is happening, or whether that's communicating with stakeholders and data users about how and where they access data. Again, because if we're all using similar language, then we can start talking across basins in a way that's going to be much more effective. And finally, none of this happens without money, so partnered approaches to figuring out how we can work together to secure funding and leverage one another's work rather than ending up competing with one another. So thanks for your time. If anyone wants to reach out to me after today, this is where to find me. And if you want to see the data, this is where to find the data, with the small caveat that with the 5G cellular changeover, some of my stations are not currently transmitting, but will be soon.
Yeah, thank you, Elise. And now for Madison and Nicole.
Thanks, Brendan. Bear with me, I have my notes on a cue card here. My name is Madison Muxworthy. I'm the Soil, Moisture, Water, and Snow Program Manager at the Yampa Valley Sustainability Council in Northwest Colorado. I'm going to be co-presenting today with my colleague Nicole Pepper, and so she's going to come up here in a couple of moments and take us through a couple more steps. We're going to be talking about our development of a soil moisture monitoring network in the Yampa River Basin. So first here, I'll just orient you to the basin in case you're not super familiar with it. The white line you can see here is the outline of the Upper Yampa River Basin. This is a snowmelt-driven watershed, and so our hydrology is very reliant on our snowmelt. You'll see the headwater area in like the Yampa over here, and then further down towards Craig, we have really heavily forested areas in the basin, and then it spans towards sagebrush down the basin, and our elevations range from greater than 12,000 to less than 6,000 feet in elevation. The main river is the Yampa River, and it's still considered to be relatively free-flowing in that it maintains its natural hydrograph because it's not impeded by major dams or trans-mountain diversions, like a lot of other places in Colorado. We have small storage projects, but they're a lot smaller than other places. Here, I would like to highlight that in this basin, we're already experiencing a less predictable water supply. We have had 3 calls on the main stem of the Yampa River. The first occurred in 2018, then shortly after in 2020, and then again in 2021. The basin is designated as overappropriated pretty much throughout the basin. We have been listed as a 303D listing by the state for extremely high river temperatures on the Yampa, and like much of the west, we're battling aridification. All of this is really stressful for a basin that relies on snowpack for our hydrology. And so less in snowpack, drier soils, and increasing evaporative loss are all really stressful to the basin. And an example of this is in the water year 2021. We had a basin average snowpack of 89% of median, but our stream flows only translated to 30% of normal. And so all of this is really pushing us towards the fact that we need more observational networks that are representative of what's happening in the basin. Here, I would like to highlight that this project is really collaborative. Our project team is listed here. You'll see these people throughout the conference today. And our PI is Marty Ralph, who's leading our team. And this would not be possible without our great project team that we have listed here. I think that this project really highlights the essentialness of pairing together Tier 1 research centers, NGOs that really know a specific area, local community colleges, and then a water user or water district together to create science that's usable for practitioners. And then just I wanted to highlight briefly that all of these partnerships have been really successful in other endeavors as well. Elise had mentioned that we started a summer research internship, which was really exciting, and that's been going on. We're gonna go into our 4th year of that. And we also co-organize a water conference in the Yampa. And thank you as well to the Upper Yampa for initial funding for this project. So here you'll see listed our project goal, and I'll just read it out for you quickly, which is to establish a new long-term soil moisture measurements to provide data and scientific insight into the reduction of runoff by dry soils, to provide a continuous record of changing landscape conditions with a changing climate, and to support operational model and forecast improvements. We were really specific about this goal, and I think that this has been a really key point of our project and staying really true to this goal. Today, our talk is gonna go over 2 components of our network process. It's not gonna be fully comprehensive of everything that we did, but we're going to talk about how we determined observational enhancement opportunities through assessing existing observational opportunities with stakeholder interviews, and to better understand data gaps from stakeholders, and to provide information that's not currently captured. And then secondly, Nicole will come up to talk about our assessment of land and surface and atmospheric factors that influence soil moisture variability. And I wanted to just highlight here, you'll see on the end portion of this, we have a larger vision, which is to install a network of these stations. And so we've installed 1 station this past September, which has been really exciting. But our larger vision is a network of these stations. And we've been doing this in a really collaborative way. So we're really excited about that. Here, I will just briefly walk you through this map. This is highlighting the pre-existing observational stations that were present in the Yampa River Basin. We use this map to identify what data is currently being captured in the Yampa, and then assess opportunities and see if there was any data gaps that we could fill, or see if there's opportunities to co-locate with existing stations to leverage existing stations. So this is, again, just the Yampa River Basin. You'll see a lot of USGS stream gauges, QuagMet stations, the Desert Research Institute, Storm Peak Lab, and then SNOTEL sites as well in there. And 3 of the SNOTEL sites also measure soil moisture. Here, I would like to highlight that we had strategic stakeholder meetings as part of our design process, and this was really key in understanding data gaps that stakeholders are needing in order to make our network really effective. And so we met with various partners throughout this phase, including the Aspen Global Change Institute, NRCS, US Forest Service, and a bunch of others, and those meetings were super valuable in how we designed our network and placed our first station. So here I'll just highlight 2 of our primary stakeholders that we met with, which is the Upper Yampa Water Conservancy District and the Colorado Basin River Forecast Center. And a key takeaway from the Upper Yampa Water Conservancy District is that they're using SWE from 2 SNOTEL sites, which are currently just outside of our basin, and they're using these to make management decisions inside of the basin. And that these are starting to work less and less well. And the Colorado Basin River Forecast Center, they identified that we should look at the middle elevation of our basin because they have found some gaps in that area. And they had also found that some of the SNOTEL sites don't go deep enough for their forecasting needs. And so the soil moisture isn't very useful for them from the SNOTEL sites currently. And my main point here is that essentially all of these forecasts aren't lining up with decision makers' needs. And so this was a really key point in determining how we were going to go about designing our network and then doing our basin analysis, which I will now pass it to Nicole, and she's going to talk about that process.
Great, thank you, Madison. Awesome. So I am going to be taking us into the next stage of our design process. And again, we're just in the designing stages in building this network. So there's been a question that I'm sure is at center of a lot of your minds. It's definitely been at center of our minds as we have been going through this process. And it's how can we design this network, put these stations in a way that captures comprehensive representation of the basin at large. We all know that precipitation is surely variable across any given landscape, and that's even more true for soil moisture. That's variable at even a finer scale. So to even get at this question, we first really just had to take a step back, look at the basin as a whole, in order to be able to get an idea of what representative even means for our basin. And to do this, we took a look at a few GIS layers, did some analysis to help us get at that question. Primarily, we assessed land surface factors and also atmospheric factors, all that contribute to and influence the way that soil moisture varies across the landscape. And today, we don't have too much time, so I'll just be highlighting some of the selected works from this analysis that is ongoing. So the first one that I'm going to be talking about is the way that we took a look at assessing land surface factors in the basin. And to do this, we performed something called a cluster analysis, and this is a method that CW3E has actually previously done in designing one of their networks in California. And basically what this does is you look at different GIS variables, and it uses a computer unsupervised machine learning algorithm, which basically groups a given area by the relationship between those variables. So we're basically grouping like areas. And in this case, we looked at 5 different variables that are all primary drivers in the surface water budget or soil moisture. The first of which was looking at precipitation. So for this, we looked at total annual precipitation, or the 30-year normal, from 1981 to 2010, and this is a data product offered by Prism Climate Group. And I'll talk a little bit more about Prism Climate Group later. But this is basically just to give us an idea of general water inputs into the soils. Additionally, we looked at a few different topographic variables, including elevation and slope, both of which help us better understand how water moves through the landscape. We looked at aspect as well, which helps us understand solar loading onto a given surface, how that varies. And lastly, we wanted to look at vegetation, and to do this, we looked at normalized difference in vegetation index, which was calculated from Landsat 8 imagery from 2020. And that's just was basically used as a proxy for understanding what sort of vegetation is on the surface. So this shows a map of our cluster analysis. We have 8 different clusters, all shown in unique colors. And for the purpose of today's discussion, I'm not going to go into the nuances of what the variable ranges are for each of those clusters. But what I do want to point out is that there's a table with the summaries for each of the clusters. And basically, if the summaries are highlighted in a common color, that means that in one or more of the variables, there's overlapping ranges. There's overlapping ranges for one or more of the variables. And in the case of our cluster analysis, most of the time that was precipitation and elevation. So what pushed the computer to put these into a different cluster or unique cluster was outerlying ranges in the other variables, so aspect, NDVI, or also slope. And this is, I think, where the clusters become helpful, more so than maybe just looking at like a simple elevation gradient, because we know that all of those variables do play an important role in soil moisture variability. So basically moving forward, we're able to use the cluster analysis to kind of just help understand, where water collection zones are, what characterizes the different subbasins. It helps us get a kind of a general framework for areas to target when we are putting the observations in. And then as a whole too, it helps us get to that question of what's representative. So when we place a station, we can make sure that we're considering the different surface characteristics. So beyond land surface characteristics, we also wanted to look at atmospheric drivers of soil moisture variability. And we did this by taking a further look at the Prism Climate Group's data. And I'll talk a little bit more just about that Prism climate data. So they provide modeled precipitation and temperature data sets. And those are basically created from observations. And they use a ton of different quality control measures, including elevation, lots of other atmospheric variables from those stations to predict these models. But they're definitely not perfect. So this is just kind of a way for us to look into it, but again, it's modeled, so not totally perfect. This is comparing the 30-year norm data set for precipitation from 1981 to 2010, so that data product with the most recent decade that they offer from 2011 to 2019. And the map on the left shows the change in annual total precipitation between those two time periods. And what we found really interesting about this map, so basically the scale goes from negative change, shown in red, to relative to our basin, it just went basically nearly to zero change or just above positive zero change. So really, what we found interesting was that it did show down in the south. That's actually where the flat tops wilderness area is, and I think Maddie actually pointed it out earlier, and this is actually where it's highlighting for an area of negative change in annual total precipitation is a really important water producing area for the Yampa River Basin. So us seeing this, it's concerning. It's at the headwaters of the Yampa, and also I think, yeah, that's mostly what I want to say about that. And then on the right-hand side, you see this is a map of the change in annual days of precipitation. And basically the scale on this one shows negative change in days or less than days in red, and then positive days in blue. Once again, and just generally, it's very variable across the landscape. And what these maps are really just meant to illustrate is that we're seeing variable and unpredictable rates of change throughout the upper Yampa. And we don't really know the true variability, so it just really emphasizes the importance of getting more observations out there. Yeah. So I'll just quickly review kind of the main things from what we've seen and what we've learned through this assessment. So I'm gonna go to my notes really quick just to make sure I take it away. So from here, we're going to be using these maps, the also ongoing modeling work that we're doing to, one, prioritize areas to focus on for instrumentation, and then also to make sure that when we're placing these stations, we're putting them in a way that's comprehensive and representative of the basin as a whole, so as to make it as useful for both water and land managers for the region. And where are we at now in the process? We're really excited to share that in September, we installed our first station. This one's named Stagecoach Ski East, and it is shown in this black dot right there. We're really excited about this location, and we settled on it for a number of reasons. One of which, it being in the headwaters of the Yampa River, so it's in the basin, the sub-basin that's at the headwaters. So it's important for our water managers. Also, it sits as an input into Stagecoach Reservoir, which, as you've heard, is one of the major reservoirs and is the major storage reservoir on the Yampa River. It also falls into the mid-elevation band, which was suggested to be focused on by our stakeholders. So it's at 9,488 feet. And also just taking a look at the map where there's existing operations, it fills a geographic gap too in observations. So we're really excited about this station, and we kind of just see it as like an important anchor for a growing network, and look forward to getting more into the ground. So I think Maddie's gonna take it home really quick.
Thanks. And we just have 2 more slides if you just want to run through them for me, or I can do it. Maybe go back. Perfect. That's it? Yeah, that's it. Awesome. So just in summary, today we only talked about 2 portions of our process with this basin analysis and our process to date. And so I just wanted to make note of that. As you can tell, our process was really rigorous, and we tried to stay really true to our goal. And so I think that's unique with our station. We see opportunities to leverage existing stations in the basin that are already there, and work with our partners that we have that have been doing this work for a long time. And so that's exciting. We look towards those opportunities. The land surface and atmospheric factors were really helpful in our analysis and ultimately helped us prioritize areas to place our first station. And we'll definitely use that information as we build out this station. And like I said earlier, our larger vision is a network of these stations with hopefully 25 stations throughout the Yampa River Basin. Awesome. And in the spirit of collaboration, I just wanted to leave us with a few of our points that we're thinking about. Like I said a little while ago, continuing to look for those opportunities to work with partners that have been doing this for a long time, leverage the expertise that's already there. I think that it would be great to get more input from water users, specifically agricultural, from the agricultural sector. That would be great. We're also trying to consider applications for these data other than the purpose that they've necessarily been cited for right now. And so specifically thinking about land management decision-making needs and applications like those. And we also love the exchanges that we've had with AGCI and other partners in CW3E, and just exchanging lessons learned from those other networks. And talking to what Elise had already shared, I think there's a huge opportunity to leverage our partnerships that we have created to seek funding and then scale up our impact together. So that's all we have today. Thanks.
Great, thank you, Madison and Nicole. And next we have Kerstin Paulsson, and followed by Duncan. Both of them are from the Scripps University, or how did I mess it up so many times? Scripps Institute of Oceanography at UC San Diego, Center for Western Weather and Water Extremes. There you go.
Thanks, Brendan. Yeah, that's a mouthful. So Duncan and I are from the Center for Western Weather and Water Extremes. And just to give you a little bit of context, we have field campaigns and observational networks throughout several watersheds in California. And as Maddie and Nicole just mentioned, we installed our first soil moisture station in collaboration with our local partners in Colorado this September. And I'll talk about that in a little bit of I forgot to use my slides. How do I advance it? Oh, too fast. Okay. Yeah, I'll talk about that and our data availability, and then I'll hand it over to Duncan to talk about our FIRO program and partnerships in that, and how we can use that to bridge the gap between these on the ground or in the field science and decision makers. And so to pick up where we left, where Nicole and Maddie left off, this is our, should I wait? Okay. I'm gonna preview all my slides. All right. So to leave where they left off, or start where they left off, this is our final site location, and as Nicole said, this is in the upper Yampa headwaters, the Huck 10 region, and within that, it's in the Yampa above Stagecoach middle elevation band. And if you were in Andy's talk earlier today, that describes the whole watershed area above Stagecoach Reservoir. And the middle elevation band within that area was determined as a priority in siting discussions with Colorado Basin River Forecast Center and Upper Yampa Water Conservancy District. And it's also in Cluster 7, and that matches the elevation target band and adds cluster diversity to existing stations existing stations nearby. And this area currently isn't instrumented either. This whole, I wish I had a laser, but the whole high elevation band, kind of around where the cluster 7 clustering is, south of the location. There's no other instrumentations up there, so it's we're pretty excited to add some coverage in this area. So this is Stagecoach Ski East. It's a picture of the station and all its assets. We have a full suite of meteorological instrumentation, and it's collecting data every 2 minutes, with the exception of the snow depth, which is every 15 minutes. So if Ryan thought he was doing overkill at 5 minutes, we have a 2-minute data. And yeah, and also to reiterate what Ryan said, at these rates, you can really see the soil react to different precipitation rates and what happens when we reach certain precipitation rate thresholds. And we can also see the lag the soil moisture has as that precipitation inundates the ground. And yeah, in our existing networks in California, we have been able to observe when we reach flood and mudslide conditions. But equally, or I would say more important than some of that near real-time capability during weather event timescales is our ability to understand antecedent soil moisture conditions in an area before big events or before the snow flies, which, as we heard earlier, affects spring runoff. And we measure at 6 depths. We really like our vertical profiles. And these depths match NRCS depth norms with the addition of a 6-inch depth. So we have 2, 4, 6, 8, 20, and 40 inches. And we chose these depths to optimize our data comparability with nearby NRCS no-tell stations and complement their existing network. And this brings up a takeaway from this slide, is that in planning we had a lot of discussions with partner agencies on existing networks in this basin, and that's a really important part of developing partnerships with data collectors. These discussions can include things like sensor choices, install protocols and maintenance protocols, and why were these choices made? Why did they choose certain sensors or install them the way they did? And so in developing a new network, that helps us decide where we want to match existing networks and where we don't want to match existing networks. And this could be for a variety of reasons, like different station priorities, different budgets, different staff availability for install and maintenance. And so a lot affects how a new network is developed. Is that me? And data collectors and data users can all benefit from these discussions and collaboration, and it helps us ultimately better interpret the data. And speaking of data, you can find our data from this station and all of our other stations at CW3E on our website at cw3e.ucsd.edu. Here's a sample plot of, and this is updated hourly. And we also disseminate to MESA West and NOAA Physical Science Laboratories Profiler Network Data and Image Library. I practiced that. And that's the sample table from MESA West's site. And for us, it's really important to ask our data users what their access needs are. In California, we put all of our sites on CDEC, the California Data Exchange Center, and that's at the request of the California-Nevada River Forecast Center. And in here in Colorado, we consulted Colorado Basin River Forecast Center, and they said they'll grab it straight from MESA West. That's the easiest for them, so that's great. And so my takeaway from this slide is that with our networks, our goal is to make sure our data is easily and widely accessible as possible for all data users. And this maximizes potential utility. As was mentioned earlier, there's a lot of opportunity, research opportunity when data is easily accessible. And we could use it for things like forest studies, fire mitigation, ecological studies, integration with ASO, remote sensing technologies, or satellite data product ground truthing. And that's all I have, so I will hand it over to Duncan.
Thank you. We're going to take a quick trip to California to provide additional context on how these enhancements in monitoring, specifically soil moisture in this case, end up with making big impacts. So this is an example of that. I'd like to highlight the FIRO program, which is a program that started in Lake Mendocino 8 years ago in the Russian River, which is in Sonoma County in North California, with the aim to make better use of existing infrastructure we have inherited and apply modern technology to increase water supply. FIRO, which stands for Forecast Informed Reservoir Operations, is an operation strategy that better informs decisions to retain or release water by integrating flexibility in operational procedures with enhanced monitoring and improved weather and water forecasts. So the important terms there, the key components are enhanced monitoring and improved forecasts. So this concept only works if we invest in those enhancements that include monitoring and improving the forecast. In order to do that, we have to better predict the synoptic situation that's causing the meteorological elements that produce precipitation. We have to invest in understanding better the microphysics of how precipitation forms. We have to invest in the interactions of snowfall and rainfall on the terrain and how that in turn turns into runoff and water supply. There are data gaps there that need to be filled in, and we address those data gaps by enhancing our observations. So we have made big investments in, for example, measurements of the West Coast over the Pacific, where we fly 3 aircraft that are sampling the weather systems that produce these large precipitation events that impact runoff. And then we have observational systems that include soil moisture and other sensors that look also at the precipitation mechanisms that and runoff mechanisms that are important for water supply in the watersheds. So this is where continued investments are needed, as well as dedicating efforts to stakeholder engagement to make all this happen. The concept behind FIRO is shown in the upper right there. What you see is a rule curve or a guide curve that is specified in a water control manual. This one is specific to Lake Mendocino. And the concept here is to manage water before the first drop hits the ground, or manage water before the first snowflake hits the ground. To achieve that, we have to develop forecasts of sufficient skill and lead time where water can be safely stored and released prior to an event. So FIRO was first demonstrated in the water year 2020 that you see there in the upper right at Lake Mendocino. And the figure shows the guide curve from the water control manual, where the water supply pool is kept low during the winter to make room for high reservoir inflows from extreme rain events. The water supply storage curve, or the guide curve, is based on water on the ground and climatology. And this was developed in the 60s, where these dams were built, and has never been updated since then. So by introducing this FIRO buffer zone, which is a pool of additional water on top of that water supply pool, we are able to manage that FIRO supply pool based on the improved forecast and the enhanced monitoring. In this particular case that you see here in this time series of how the water storage varies with the water year, we see high inflows from rain events that are managed within the FIRO pool, to the extent where at the end of the water year, FIRO operations result in 20% more additional water supply, which is the figure there that you see in the upper right, which corresponds to about 11,000 additional acre-feet in a time that we were entering a severe drought in 2020, where it was the 3rd driest year on record. So by working on enhanced modeling, developing our models, it produces enhancements in our estimates of precipitation, which results in improved water storage. So in 2021, this is the situation where we entered the drought condition, and Governor Newsom declared a drought emergency in California, but also noted that Lake Mendocino, where he's standing at, had an additional 50% of more water entering that drought. So this just demonstrates how this investment in enhanced monitoring and developing models can improve our water supply in the situations where we switch from flood to drought so frequently with the climate change impacts that we're experiencing. So this has attracted the attention of politicians at the federal level, at state level and local level, and this program has grown tremendously. We have now 4 sites. In addition to Lake Mendocino, the Russian River, we are also working on Lake Sonoma, which is right by Lake Mendocino, so I'm applying lessons learned there to Lake Sonoma. We have a pair of reservoirs, New Ballards Bar and Oroville Dam on the Yuba Feather, which are impacted heavily by snow, where we've been testing FIRO. In Southern California near Los Angeles, we have Prado Dam, where storm water that's released through a FIRO operation actually ends up being recharged in the ground through a managed aquifer recharge program that is managed by the Orange County Water District. And we're just starting to work at Howard Hansen Dam in Washington by Seattle on the Green River. So these sites are all unique, and forecast skill and lead time vary, which emphasizes the need for monitoring and model development at these sites, the need for research and the need for a research and operations partnership. So lessons learned from FIRO that applies here. FIRO makes better use of existing infrastructure. We apply modern technologies to make these structures more resilient, and we do that without pouring any additional concrete in our landscape. So it's a very effective way of using what we have. Precipitation and stream flow forecasts have improved as a result of investments in monitoring, modeling, and research. And this is setting important policy changes where we start introducing technology and improvements and forecasts in our water control manuals, which requires a strong engagement with our agency partners. So we have worked on developing this research and operations partnership, which is a process that involves a long-term framework that has enabled breakthrough advances in research and prediction that change policy for improved practical outcomes. It does require us to be pushy in our research, and by what I mean by that is that we need to push the research to operations and also pull the operations into the research with minimal complex and bureaucratic transactions. This requires an open and trusted relationship between the partners. We do that by holding project-specific steering committees within each of our sites that include local water agencies and also federal partners such as the Bureau of Reclamation, U.S. Army Corps, National Weather Service, where we impose research questions to advance our feasibility process, that is the operational pull onto the research, and develop research and technologies to improve our viability assessment, and that is the push of the research into operations. So using this concept, the analogy here is, could an expanded soil moisture network and an improvement in forecast skill assist with water supply in the Colorado River? Thank you.
Well, we've going longer than we had expected. We just are so excited about our projects. I'm going to ask the panelists to come up here real quick and sit down. We have about 5 minutes for questions.